So I'm going to try to cover a lot in this, the astrochemical principle of planet formation and stellar evolution according to stellar metamorphosis. I wrote this back in 2019, February. And then I also have the Gravichemical principle. I had fun naming that. July 23rd, 2016, I wrote that a bit earlier. But they're still true. They still apply for this theory to be developed fully. Hi, Celeste. For this paper, I have some new concepts. I don't know if people have been reviewing this stuff, but the Gravichemical principle, what this means, it says here, in stellar metamorphosis, planets and exoplanets are evolving in dead stars. The Gravichemical principle is a short term used to represent the idea that chemical reactions during stellar evolution are reliant on the energy provided by the gravitationally collapsing star. So as the star cools and evolves and collapses on itself, the energy from that collapse fuels the energy required to make chemical reactions occur on large scales. And being that the gravitational fields of stars are very, very strong and they collapse over billions of years, you can do a lot of chemistry with that. You can do a lot of work. And the principle is the activation energy required for most chemical reactions on a star are fueled indirectly and directly by gravitational collapse. And in essence, the fact that there are huge amounts of chemicals on the Earth in the form of crystalline structure called rocks and minerals is direct observational evidence that all stars gravitationally collapse and engage in huge amounts of chemistry. And the activation energy is a chemistry number. So you have the energies, this is energy going up, and this is the timeline. For endothermic reactions, you have the energy of reactants, and the activation energy is supplied by gravitational collapse, so the star is crushing itself, combines the elements together to make more complex molecules that have more energy as a complete unit. For instance, when you combine hydrogen with carbon, that would be a combination reaction, which is probably endothermic, and that forms methane. And that's what stars do. They form methane and natural gas naturally. But and that's what late stage stars are doing when they form the carbon with all the hydrogen that's available. Is they form hydrocarbons abiotically, meaning without biological organisms needed. And also you have exothermic reactions. So you have the energy of reactants, and you have your activation energy, and then you release more energy. So here's energy release here at the end, which is the total energy of the products after they've been disintegrated, after the reaction occurred, in other words. So you gain energy with endos and you lose energy with the exos. Think of the exothermic reaction, heat releasing, and endo, heat absorbing. And gravitational collapse fuels both types of those reactions. That's activation energy, a gravichemical principle. And for those who are new, the star starts out up here, collapses on itself, and fuels all the chemical reactions required to form the planet with the rocks and minerals. So I don't know if Celeste is wondering about this, but that's why I like rocks and minerals. They are crystalline form. The crystalline form of an ancient star. It's when you look up at the night sky and you see those little bright dots up there. The Earth is one of those, but many billions of years old. It's so old, in fact, that the material that it's composed of forms crystalline structure. I mean, rocks. And that's it. You're holding a piece of a star every time you pick up a rock off the ground. I know it's kind of it's kind of stupid, but we're also made of the Earth, which is an ancient star. So we are essentially walking around. We're Earthlings. We're tiny pieces of the Earth. The astrochemical principle states here the majority of chemical reactions in the universe take place inside of stars as they cool and die, not in the interstellar medium. Okay. I wrote here, the purpose of this paper and statement is to redirect scientists towards stars as being the location for thermochemical, electrochemical, and photochemical reactions. They are the locations for the majority of the radiation production and chemical reactions which occur in outer space. Stars form chemicals in huge amounts, and as they die, evolve, and disintegrate themselves and other older stars, the material then floats about in the interstellar medium after the fact as a result of their evolutionary processes. Any studies that ignore stars as being the locations for the majority of chemical synthesis and or decomposition reactions is misguided. So the reason why I wrote this paper was that mainstream scientists, they still sort of have it in their mind that young stars like the sun are these fantasy fusion reactors. They're not. They're huge chemical furnaces. I know it seems like we're going backwards, but the actual fusion processes and the high energy phenomenon belong inside of active galaxies and quasars and stuff like that. That's where the actual element creation is occurring, not inside of stars. Stars are these giant chemical furnaces that form planets, that form life, that form every single chemical compound that we're familiar with. And they do that with gravitational collapse. So after the star is fully formed, of course, it doesn't form with gravitational collapse. The formation process of a star is incredibly electromagnetic. It's a very complex process. I don't want to talk about that here, but after it's born, then it keeps the material there with the gravitational field, and that material slowly is dissipated and transforms itself and undergoes all the chemical reactions and physical reactions necessary to form a planet. It's a very, very different worldview than what the mainstream scientists are saying. They're saying that these are the fusion reactors, and then these just pop up out of a big disk, so they just separate them two. These form in a big disk, and then these are just these fusion reactors. But they're not fusion reactors, they're young Earths, all of them. And I got another email. I wanted to correct them, I guess, in a nice way. I don't like arguing. I just state what I have to state, and if somebody has a problem with it, then there's nothing I can do. But he had shown me a paper that Mr. Crothers and Robitaille have written. And at the very bottom, he says, the stars are condensed matter, and the mass-luminosity relationship is invalid. Two corrections. He says the stars are condensed matter. Well, that's not exactly true. When the stars are young, they're not condensed matter. When stars are young, they're plasma, and that plasma phase transitions to gaseous material, and the star becomes condensed matter as it evolves. So only the old stars are condensed matter. So when he says the stars are condensed matter, he's probably talking about the young ones. He's not talking about the old ones because he considers the old ones as being a completely different object called a planet. But that's what planets are. They are condensed matter stars. The star becomes condensed matter as it evolves. So up here, it's not condensed matter. It's plasma, which transitions to gaseous matter, which then transitions to liquid and solid material, which is condensed matter. Two, he says the mass-luminosity relationship is invalid. Partially invalid. And the reason why I say that is the mass-luminosity relationship was invented before the discovery was made that old stars are mislabeled planets. So the mass of a young star is really big, and its luminosity is really, really high. And as it loses mass, it loses its luminosity, but then there reaches a point to where it no longer shines strongly in the visible spectrum, moves into the thermal spectrum, which is around brown dwarf stages. And then it continues going all the way down, and it internalizes the heat. So the leftover heat from earlier stages of evolution gets internalized. So when they stop shining, it isn't that the mass luminosity relationship stops being valid, what happens is that luminosity, that heat radiation, internalizes. So there needs to be a method to say, well, that still the more massive objects such as Jupiter are still going to be hotter in their interior versus something like Neptune or Uranus. And Neptune and Uranus are still going to be hotter than something like the Earth in their interiors because they have much larger gravitational fields. They can compress that matter to much hotter temperatures internally, even though regardless if they don't shine like a young star does. They're very, very old stars. Jupiter, I think, is around 700 million years old. Neptune and Uranus, respectively, 1.1 and 1.2 billion years old, and the Earth 4.5 plus billion years old. But so the mass luminosity thing, it just shows the time too. Like back when Eddington's day, they were always classifying stars as shining only. So when they draw up, a luminosity mass relationship, they sort of don't have the big picture. So it sort of becomes more of an abstraction, and then they use it to try to apply to everything, which isn't really the best thing to do, because then it becomes a dogma, and then when you have the discovery such as it's happening right now, it gets that much harder to correct it after the fact, because it's already canonized. In other words, it's already in the textbooks. Everybody already believes that if anybody has any problems against it, then there's nothing you can do. Everybody already thinks it's some written in stone rule. Anyways, I'll link these two papers to the bottom: the Gravichemical principle and the Astrochemical principle. And the Astrochemical principle, again, the reason why I state that is because astronomers, they sort of look at the chemistry of the universe, the chemistry of a galaxy happening in the interstellar medium, in the vacuum. I'm like, no, it happens exactly where you're observing it to happen. It's inside of stars as they cool and collapse on themselves. And the planets are direct observational evidence. You can take your hand and put it in the dirt and pick up a piece of a star, a very, very old star, if you want to. That's direct observational evidence that that's exactly what happens. Calling it a planet and separating the two in your mind is where the astronomers are really having a hard time. All right, guys, take it easy.